Reflections on the motive power of heat and on machines fitted to develop that power. By Sadi Carnot. Footnote. Sadi Carnot's Réflexions sur la puissance motrice de feu, Paris, Barclay, 1824, was long ago completely exhausted. As but a small number of copies were printed, this remarkable work remained long unknown to the earlier writers on thermodynamics. It was, therefore, for the benefit of savants unable to study a work out of print, as well as to render honour to the memory of Sadi Carnot, that the new publishers of the Annales scientifiques de l'École normale supérieure second series, Volume 1, 1872, published a new edition from which this translation is reproduced. End footnote. Everyone knows that heat can produce motion. That it possesses vast motive power, no one can doubt. In these days, when the steam engine is everywhere so well known. To heat also are due the vast movements which take place on the earth. It causes the agitations of the atmosphere, the ascension of clouds, the fall of rain, and of meteors, the currents of water which channel the surface of the globe, and of which man has thus far employed but a small portion. Even earthquakes and volcanic eruptions are the result of heat. From this immense reservoir we may draw the moving force necessary for our purposes. Nature, in providing us with combustibles on all sides, has given us the power to produce, at all times and in all places, heat, and the impelling power which is the result of it. To develop this power, to appropriate it to our uses, is the object of heat engines. The study of these engines is of the greatest interest. Their importance is enormous, their use is continually increasing, and they seem destined to produce a great revolution in the civilized world. Already the steam engine works our mines, impels our ships, excavates our ports and our rivers, forges iron, fashions wood, grinds grains, spins and weaves our clothes, transports the heaviest burdens, etc. It appears that it must some day serve as a universal motor and be substituted for animal power, waterfalls, and air currents. Over the first of these motors it has the advantage of economy. Over the two others, the inestimable advantage that it can be used at all times and places without interruption. If, some day, the steam engine shall be so perfected that it can be set up and supplied with fuel at small cost, it will combine all desirable qualities, and will afford to the industrial arts a range the extent of which can scarcely be predicted. It is not merely that a powerful and convenient motor that can be procured and carried anywhere is substituted for the motors already in use, but that it causes rapid extension in the arts in which it is applied, and can even create entirely new arts. The most signal service that the steam engine has rendered to England is undoubtedly the revival of the working of the coal mines, which had declined, and threatened to cease entirely, in consequence of the continually increasing difficulty of drainage and of raising the coal. Footnote. It may be said that coal mining has increased tenfold in England since the invention of the steam engine. It is almost equally true in regard to the mining of copper, tin, and iron. The results produced in a half-century by the steam engine in the mines of England are today paralleled in the gold and silver mines of the New World, mines of which the working declined from day to day, principally on account of the insufficiency of the motors employed in the draining and the extraction of the minerals. End footnote. We should rank second the benefit to iron manufacture, both by the abundant supply of coal substituted for wood just when the latter had begun to grow scarce, and by the powerful machines of all kinds, the use of which the introduction of the steam engine has permitted or facilitated. Iron and heat are, as we know, the supporters, the bases of the mechanic arts. It is doubtful if there be in England a single industrial establishment of which the existence does not depend on the use of these agents, and which does not freely employ them. To take away today from England her steam engines would be to take away at the same time her coal and iron. It would be to dry up all her sources of wealth, to ruin all on which her prosperity depends, in short, to annihilate that colossal power. The destruction of her navy, which she considers her strongest defence, would perhaps be less fatal. The safe and rapid navigation by steamships may be regarded as an entirely new art due to the steam engine. Already this art has permitted the establishment of prompt and regular communications across the arms of the sea and on the great rivers of the old and new continents. It has made it possible to traverse savage regions where before we could scarcely penetrate. It has enabled us to carry the fruits of civilization over portions of the globe where they would else have been wanting for years. Steam navigation brings nearer together the most distant nations. It tends to unite the nations of the earth as inhabitants of one country. In fact, to lessen the time, the fatigues, the uncertainties, and the dangers of travel, is not this the same as greatly to shorten distances? Footnote. We say to lessen the dangers of journeys. In fact, although the use of the steam engine on ships is attended by some danger, which has been greatly exaggerated, this is more than compensated by the power of following always an appointed and well-known route, of resisting the force of the winds which would drive the ship towards the shore, the shoals, or the rocks. End footnote. The discovery of the steam engine owed its birth, like most human inventions, to rude attempts which have been attributed to different persons. While the real author is not certainly known, it is, however, less in the first attempts that the principal discovery consists, than in the successive improvements which have brought steam engines to the condition in which we find them today. There is almost as great a distance between the first apparatus in which the expansive force of steam was displayed and the existing machine as between the first raft that man ever made and the modern vessel. If the honor of a discovery belongs to the nation in which it has acquired its growth and all its developments, this honor cannot be here refused to England. Savary, Newcomen, Smeaton, the famous Watt, Wolfe, Trevithick, and some other English engineers are the veritable creators of the steam engine. It has acquired at their hands all its successive degrees of improvement. Finally, it is natural that an invention should have its birth, and especially be developed, be perfected, in that place where its want is most strongly felt. Notwithstanding the work of all kinds done by steam engines, notwithstanding the satisfactory condition to which they have been brought today, their theory is very little understood, and the attempts to improve them are still directed almost by chance. The question has often been raised whether the motive power of heat is unbounded. Whether the possible improvements in steam engines have an assignable limit, a limit which the nature of things will not allow to be passed by any means whatever, or whether, on the contrary, these improvements may be carried on indefinitely. Footnote. We use here the expression motive power to express the useful effect that a motor is capable of producing. This effect can always be likened to the elevation of a weight to a certain height. It has, as we know, as a measure, the product of the weight multiplied by the height to which it is raised. End footnote. We have long sought, and are seeking today, to ascertain whether there are in existence agents preferable to the vapor of water for developing the motive power of heat. Whether atmospheric air, for example, would not present in this respect great advantages. We propose now to submit these questions to a deliberate examination. The phenomenon of the production of motion by heat has not been considered from a sufficiently general point of view. We have considered it only in machines the nature and mode of action of which have not allowed us to take in the whole extent of application of which it is susceptible. In such machines the phenomenon is, in a way, incomplete. It becomes difficult to recognize its principles and study its laws. In order to consider in the most general way the principle of the production of motion by heat, it must be considered independently of any mechanism or any particular agent. It is necessary to establish principles applicable not only to steam engines, but to all imaginable heat engines, whatever the working substance and whatever the method by which it is operated. Footnote. We distinguish here the steam engine from the heat engine in general. The latter may make use of any agent whatever, of the vapor of water, or of any other, to develop the motive power of heat. End footnote. Machines which do not receive their motion from heat, those which have for a motor the force of men or of animals, a waterfall, an air current, etc., can be studied even to their smallest details by the mechanical theory. All cases are foreseen. All imaginable movements are referred to these general principles, firmly established and applicable under all circumstances. This is the character of a complete theory. A similar theory is evidently needed for heat engines. We shall have it only when the laws of physics shall be extended enough, generalized enough, to make known beforehand all the effects of heat acting in a determined manner on any body. We will suppose in what follows at least a superficial knowledge of the different parts which compose an ordinary steam engine, and we consider it unnecessary to explain what are the furnace, boiler, steam cylinder, piston, condenser, etc. The production of motion in steam engines is always accompanied by a circumstance on which we should fix our attention. This circumstance is the re-establishing of equilibrium in the caloric. That is, its passage from a body in which the temperature is more or less elevated to another in which it is lower. What happens, in fact, in a steam engine actually in motion? The caloric developed in the furnace by the effect of the combustion traverses the walls of the boiler, produces steam, and in some way incorporates itself with it. The latter, carrying it away, takes it first into the cylinder, where it performs some function, and from thence into the condenser, where it is liquefied by contact with the cold water which it encounters there. Then, as a final result, the cold water of the condenser takes possession of the caloric developed by the combustion. It is heated by the intervention of the steam, as if it had been placed directly over the furnace. The steam is here only a means of transporting the caloric. It fills the same office as in the heating of baths by steam, except that in this case its motion is rendered useful. We easily recognize in the operations that we have just described the re-establishment of equilibrium in the caloric, its passage from a more or less heated body to a cooler one. The first of these bodies, in this case, is the heated air of the furnace. The second is the condensing water. The re-establishment of equilibrium of the caloric takes place between them, if not completely, at least partially, for on the one hand the heated air, after having performed its function, having passed round the boiler, goes out through the chimney with a temperature much below that which it had acquired as the effect of combustion. And on the other hand, the water of the condenser, after having liquefied the steam, leaves the machine with a temperature higher than that with which it entered. The production of motor power is then due in steam engines not to an actual consumption of caloric, but to its transportation from a warm body to a cold body, that is, to its re-establishment of equilibrium, an equilibrium considered as destroyed by any cause whatever, by chemical action such as combustion, or by any other. We shall see shortly that this principle is applicable to any machine set in motion by heat. According to this principle, the production of heat alone is not sufficient to give birth to the impelling power. It is necessary that there should also be cold. Without it, the heat would be useless. And in fact, if we should find about us only bodies as hot as our furnaces, how can we condense steam? What should we do with it if once produced? We should not presume that we might discharge it into the atmosphere, as is done in some engines. Footnote. Certain engines at high pressure throw the steam out into the atmosphere instead of the condenser. They are used specially in places where it would be difficult to procure a stream of cold water sufficient to produce condensation. End footnote. The atmosphere would not receive it. It does receive it under the actual condition of things, only because it fulfills the office of a vast condenser, because it is at a lower temperature. Otherwise, it would soon become fully charged, or rather, would be already saturated. Footnote. The existence of water in the liquid state here necessarily assumed, since without it the steam engine could not be fed, supposes the existence of a pressure capable of preventing this water from vaporizing, consequently of a pressure equal or superior to the tension of vapor at that temperature. If such a pressure were not exerted by the atmospheric air, there would be instantly produced a quantity of steam sufficient to give rise to that tension, and it would be necessary always to overcome this pressure in order to throw out the steam from the engines into the new atmosphere. Now this is evidently equivalent to overcoming the tension which the steam retains after its condensation, as effected by ordinary means. If a very high temperature existed at the surface of our globe, as it seems certain that it exists in its interior, all the waters of the ocean would be in a state of vapor in the atmosphere, and no portion of it would be found in a liquid state. End footnote. Wherever there exists a difference of temperature, wherever it has been possible for the equilibrium of the caloric to be re-established, it is possible to have also the production of impelling power. Steam is a means of realizing this power, but it is not the only one. All substances in nature can be employed for this purpose. All are susceptible of changes of volume, of successive contractions and dilations. Through the alternation of heat and cold, all are capable of overcoming in their changes of volume certain resistances, and of thus developing the impelling power. A solid body, a metallic bar, for example, alternately heated and cooled, increases and diminishes in length, and can move bodies fastened to its ends. A liquid alternately heated and cooled increases and diminishes in volume, and can overcome obstacles of greater or less size, opposed to its dilatation. An aeriform fluid is susceptible of considerable change of volume by variations of temperature. If it is enclosed in an expansible space, such as a cylinder provided with a piston, it will produce movements of great extent. Vapors of all substances capable of passing into a gaseous condition, as of alcohol, of mercury, of sulfur, etc., may fulfill the same office as vapor of water. The latter, alternately heated and cooled, would produce motive power in the shape of permanent gases, that is, without ever returning to a liquid state. Most of these substances have been proposed, many even have been tried, although up to this time perhaps without remarkable success. We have shown that in steam engines the motive power is due to a re-establishment of equilibrium in the caloric. This takes place not only for steam engines, but also for every heat engine, that is, for every machine of which caloric is the motor. Heat can evidently be a cause of motion only by virtue of the changes of volume or of form which it produces in bodies. These changes are not caused by uniform temperature, but rather by alternations of heat and cold. Now, to heat any substance whatever requires a body warmer than the one to be heated. To cool it requires a cooler body. We supply caloric to the first of these bodies that we may transmit it to the second by means of the intermediary substance. This is to re-establish, or at least to endeavor to re-establish, the equilibrium of the caloric. It is natural to ask here this curious and important question. Is the motive power of heat invariable in quantity, or does it vary with the agent employed to realize it as the intermediary substance, selected as the subject of action of the heat? It is clear that this question can be asked only in regard to a given quantity of caloric, the difference of the temperatures also being given. Footnote. It is considered unnecessary to explain here what is quantity of caloric or quantity of heat, for we employ these two expressions indifferently, or to describe how we measure these quantities by the calorimeter. Nor will we explain what is meant by latent heat, degree of temperature, specific heat, etc. The reader should be familiarized with these terms through the study of the elementary treatises of physics or of chemistry. End footnote. We take, for example, one body A kept at a temperature of 100 degrees, and another body B kept at a temperature of 0 degrees, and ask what quantity of motive power can be produced by the passage of a given portion of caloric, for example, as much as is necessary to melt a kilogram of ice, from the first of these bodies to the second. We inquire whether this quantity of motive power is necessarily limited, whether it varies with the substance employed to realize it, whether the vapor of water offers in this respect more or less advantage than the vapor of alcohol, of mercury, a permanent gas, or any other substance. We will try to answer these questions, availing ourselves of ideas already established. We have already remarked upon this self-evident fact, or fact which at least appears evident, as soon as we reflect on the changes of volume occasioned by heat. Wherever there exists a difference of temperature, motive power can be produced. Reciprocally, wherever we can consume this power, it is possible to produce a difference of temperature. It is possible to occasion destruction of equilibrium in the caloric. Are not percussion and the friction of bodies actually means of raising their temperature, of making it reach spontaneously a higher degree than that of the surrounding bodies, and consequently of producing a destruction of equilibrium in the caloric, where equilibrium previously existed? It is a fact proved by experience that the temperature of gaseous liquids It is a fact proved by experience that the temperature of gaseous fluids is raised by compression and lowered by rarefaction. This is a sure method of changing the temperature of bodies and destroying the equilibrium of the caloric as many times as may be desired with the same substance. The vapor of water employed in an inverse manner to that in which it is used in steam engines can also be regarded as a means of destroying the equilibrium of the caloric. To be convinced of this, we need but to observe closely the manner in which motive power is developed by the action of heat on vapor of water. Imagine two bodies, A and B, kept each at a constant temperature, that of A being higher than that of B. These two bodies, to which we can give or from which we can remove the heat without causing their temperatures to vary, exercise the functions of two unlimited reservoirs of caloric. We will call the first the furnace and the second the refrigerator. If we wish to produce motive power by carrying a certain quantity of heat from the body A to the body B, we shall proceed as follows. 1. To borrow caloric from the body A to make steam with it, that is, to make this body fulfill the function of a furnace, or rather of the metal composing the boiler in ordinary engines. We here assume that the steam is produced at the same temperature as the body A. 2. The steam having been received in a space capable of expansion, such as a cylinder furnished with a piston, to increase the volume of this space, and consequently also that of the steam. Thus rarefied, the temperature will fall spontaneously, as occurs with all elastic fluids. Admit that the rarefaction may be continued to the point where the temperature becomes precisely that of the body B. 3. To condense the steam by putting it in contact with the body B, and at the same time exerting on it a constant pressure until it is entirely liquefied. The body B fills here the place of the injection water in ordinary engines, with this difference, that it condenses the vapor without mingling with it, and without changing its own temperature. Footnote. We may perhaps wonder here that the body B, being at the same temperature as the steam, is able to condense it. Doubtless this is not strictly possible, but the slightest difference of temperature will determine the condensation, which suffices to establish the justice of our reasoning. It is thus that, in the differential calculus, it is sufficient that we can conceive the neglected quantities indefinitely reducible in proportion to the quantities retained in the equations, to make certain of the exact result. The body B condenses the steam without changing its own temperature. This results from our supposition. We have admitted that this body may be maintained at a constant temperature. We take away the caloric as the steam furnishes it. This is the condition in which the metal of the condenser is found when the liquefaction of the steam is accomplished by applying cold water externally, as was formerly done in several engines. Similarly, the water of a reservoir can be maintained at a constant level if the liquid flows out at one side as it flows in at the other. One could even conceive the bodies A and B maintaining the same temperature, although they might lose or gain certain quantities of heat. If, for example, the body A were a mass of steam ready to become liquid, and the body B a mass of ice ready to melt, these bodies might, as we know, furnish or receive caloric without thermometric change. End footnote. The operations which we have just described might have been performed in an inverse direction and order. There is nothing to prevent forming vapor with the caloric of the body B, and at the temperature of that body, compressing it in such a way as to make it acquire the temperature of the body A, finally condensing it by contact with this latter body, and continuing the compression to complete liquefaction. By our first operations there would have been at the same time production of motive power, and transfer of caloric from the body A to the body B. By the inverse operations, there is at the same time expenditure of motive power and return of caloric from the body B to the body A. But if we have acted in each case on the same quantity of vapor, if there is produced no loss either of motive power or caloric, the quantity of motive power produced in the first place will be equal to that which would have been expended in the second, and the quantity of caloric passed in the first case from the body A to the body B would be equal to the quantity which passes back again in the second from the body B to the body A, so that an indefinite number of alternative operations of this sort could be carried on without in the end having either produced motive power or transferred caloric from one body to the other. Now, if there existed any means of using heat preferable to those which we have employed, that is, if it were possible by any method whatever to make the caloric produce a quantity of motive power greater than we have made it produce by our first series of operations. It would suffice to divert a portion of this power in order, by the method just indicated, to make the caloric of the body B return to the body A from the refrigerator to the furnace, to restore the initial conditions, and thus to be ready to commence again an operation precisely similar to the former, and so on. This would be not only perpetual motion, but an unlimited creation of motive power, without consumption either of caloric or of any other agent whatever. Such a creation is entirely contrary to ideas now accepted, to the laws of mechanics and of sound physics. It is inadmissible. Footnote. Note A, Appendix B, end footnote. We should then conclude that the maximum of motive power resulting from the employment of steam is also the maximum of motive power realizable by any means whatever. We will soon give a second, more rigorous demonstration of this theory. This should be considered only as an approximation. See page 59. We have a right to ask, in regard to the proposition just enunciated, the following questions. What is the sense of the word maximum here? By what sign can it be known that this maximum is attained? But by what sign can it be known whether the steam is employed to greatest possible advantage in the production of motive power? Since every re-establishment of equilibrium in the caloric may be the cause of the production of motive power, every re-establishment of equilibrium which shall be accomplished without production of this power should be considered as an actual loss. Now, very little reflection would show that all change of temperature which is not due to a change of volume of the bodies can be only a useless re-establishment of equilibrium in the caloric. Footnote. We assume here no chemical action between the bodies employed to realize the motive power of heat. The chemical action which takes place in the furnace is, in some sort, a preliminary action, an operation destined not to produce immediately motive power, but to destroy the equilibrium of the caloric, to produce a difference of temperature which may finally give rise to motion. End footnote. The necessary condition of the maximum is, then, that in the bodies employed to realize the motive power of heat, there should not occur any change of temperature which may not be due to a change of volume. Reciprocally, every time that this condition is fulfilled, the maximum will be attained. This principle should never be lost sight of in the construction of heat engines. It is its fundamental basis. If it cannot be strictly observed, it should at least be departed from as little as possible. Every change of temperature which is not due to a change of volume, or to chemical action, an action that we provisionally suppose not to occur here, is necessarily due to the direct passage of the caloric from a more or less heated body to a colder body. This passage occurs mainly by the contact of bodies of different temperatures. Hence, such contact should be avoided as much as possible. It cannot probably be avoided entirely, but it should at least be so managed that the bodies brought in contact with each other differ as little as possible in temperature. When we just now supposed, in our demonstration, the caloric of the body A employed to form steam, this steam was considered as generated as the temperature of the body A. Thus the contact took place only between bodies of equal temperatures. The change of temperature occurring afterwards in the steam was due to dilatation, consequently to a change of volume. Finally, condensation took place also without contact of bodies of different temperatures. It occurred while exerting a constant pressure on the steam brought in contact with the body B of the same temperature as itself. The conditions for a maximum are thus found to be fulfilled. In reality, the operation cannot proceed exactly as we have assumed. To determine the passage of caloric from one body to another, it is necessary that there should be an excess of temperature in the first. But this excess may be supposed as slight as we please. We can regard it as insensible in theory, without thereby destroying the exactness of the arguments. A more substantial objection may be made to our demonstration thus. When we borrow caloric from the body A to produce steam, and when this steam is afterwards condensed by its contact with the body B, the water used to form it, and which we considered at first as being of the temperature of the body A, is found at the close of the operation at the temperature of the body B. It has become cool. If we wish to begin again an operation similar to the first, if we wish to develop a new quantity of motive power with the same instrument, with the same steam, it is necessary first to re-establish the original condition, to restore the water to the original temperature. This can undoubtedly be done by at once putting it again in contact with the body A. But there is then contact between bodies of different temperatures and loss of motive power. Footnote. This kind of loss is found in all steam engines. In fact, the water destined to feed the boiler is always cooler than the water which it already contains. There occurs between them a useless re-establishment of equilibrium of caloric. We are easily convinced, a posteriori, that this re-establishment of equilibrium causes a loss of motive power if we reflect that it would have been possible to previously heat the feed water by using it as condensing water in a small accessory engine, when the steam drawn from the large boiler might have been used, and where the condensation might be produced at a temperature intermediate between that of the boiler and that of the principal condenser. The power produced by the small engine would have caused no loss of heat, since all that which had been used would have returned into the boiler with the water of condensation. End footnote. It would be impossible to execute the inverse operation, that is, to return to the body A the caloric employed to raise the temperature of the liquid. This difficulty may be removed by supposing the difference of temperature between the body A and the body B indefinitely small. The quantity of heat necessary to raise the liquid to its former temperature will also be indefinitely small and unimportant relatively to that which is necessary to produce steam, a quantity always limited. The proposition found elsewhere, demonstrated for the case in which the difference between the temperatures of the two bodies is indefinitely small, may be easily extended to the general case. In fact, if it operated to produce motive power by the passage of caloric from the body A to the body Z, the temperature of this latter body being very different from that of the former, we should imagine a series of bodies, B, C, D, of temperatures intermediate between those of the bodies A, Z, and selected so that the differences from A to B, from B to C, etc., may all be indefinitely small. The caloric coming from A would not arrive at Z till after it had passed through the bodies B, C, D, etc., and after having developed in each of these stages maximum motive power. The inverse operations would here be entirely possible, and the reasoning of page 52 would be strictly applicable. According to established principles at the present time, we can compare with sufficient accuracy the motive power of heat to that of a waterfall. Each has a maximum that we cannot exceed, whatever may be, on the one hand, the machine which is acted upon by the water, and whatever, on the other hand, the substance acted upon by the heat. The motive power of a waterfall depends on its height and on the quantity of the liquid. The motive power of heat depends also on the quantity of caloric used, and on what may be termed, on what in fact we will call, the height of its fall. Footnote. The matter here dealt with being entirely new, we are obliged to employ expressions not in use as yet, and which perhaps are less clear than is desirable. End footnote. That is to say, the difference of temperature of the bodies between which the exchange of caloric is made. In the waterfall, the motive power is exactly proportional to the difference of level between the higher and lower reservoirs. In the fall of caloric, the motive power undoubtedly increases with the difference of temperature between the warm and the cold bodies. But we do not know whether it is proportional to this difference. We do not know, for example, whether the fall of caloric from 100 to 50 degrees furnishes more or less motive power than the fall of this same caloric from 50 to 0. It is a question which we propose to examine hereafter.